In this video, I'd like to talk about how we can use topology to solve equations. At first, it might seem surprising that topology could be useful here. After all, topology studies flexible objects, while equations are completely rigid. For example, take the equation x cubed minus x equals 0. The solutions occur where the curve intersects the x-axis. Now, if we deform this curve slightly, all the solutions get completely messed up. But actually, there's something that hasn't changed: the existence of solutions. So while topological tools often can't tell us what the solution is, they can tell if there's a solution. Let's introduce the main concept of this video: linking. These two loops are linked together. If they were made of some physical material, they'd be impossible to pull apart. We'd like to capture this idea mathematically. Some pairs of loops appear more entangled than others, so maybe we could measure the amount of linking. It turns out there are a lot of ways to do this, so I encourage you to pause the video and try to think about it yourself. I'll highlight 3 methods. The first is to notice that the more the loops wrap around each other, the more entangled they are, so we could count the number of wrappings. The second method is to pull the loops apart and count the number of collisions. These collisions serve as obstructions to separating the loops. The more entangled the loops are, the more collisions there will be. The final method I'll discuss is to stretch a membrane across one loop and count the number of intersections with the other. It might not be obvious what this has to do with linking, but we can show that it actually computes the same number as the previous 2 methods. Considering the first approach, each time the blue loop wraps around the red loop, it must pass through the membrane, so the number of intersections is the same as the number of wrappings. For the second approach, when we try to pull the loops apart, the intersections will collide with the boundary of the membrane, so they also correspond to the number of collisions. This final method highlights an important relationship. Linking in the boundary corresponds to intersection in the interior. So far, we haven't been using orientations, but topological intersections often don't behave nicely without them. For example, these 2 loops are completely unlinked. Yet, if we stretch a membrane across the blue loop, we count 2 intersections. Let's fix this issue. We can give the loop an orientation by choosing a direction of travel, and we can give the surface an orientation by choosing one of its 2 sides to be the top. Imagine a particle traveling along the red loop. If the particle passes from the top of the membrane to the bottom, we count that as a positive intersection. If it passes from the bottom to the top, that counts as a negative intersection. Now we see that there is 1 positive and 1 negative intersection, so the net oriented intersection number is 0, as expected. There are 2 important properties of linking. The first is that it doesn't matter which loop we stretch the membrane across, we always get the same intersection number. This is because linking is symmetric. The second is that it also doesn't matter which interior membrane we use, as long as it's orientable. However, it is very important that the membrane is orientable. For example, these 2 loops have a linking number of 2, yet if we choose a Mobius strip with only one side as the membrane, we get no intersections. Let's consider linking in 1 dimension. First, we need to know what the one-dimensional analog of a loop is. A loop is just a deformed circle, and the standard circle is the set of all points in the plane a distance of 1 away from the origin. On a line, the points a distance of 1 away from the origin are just positive and negative 1. A zero-dimensional sphere, or zero sphere for short, is just a pair of points. These zero spheres are linked together just like the loops. They are impossible to separate. In addition, if we stretch an interval across one of the zero spheres, it will intersect the other. The reason is basically the same as before. This intersection turns into a collision at the boundary when we try to separate the zero spheres. In 3D, we saw that you can pick any orientable surface to be the interior of your loop, and something similar holds in 1D as well. You can pick any continuous path to be the interior of your zero sphere, and you'll always get the same intersection number. The interval represents a straight path from one endpoint to another, but we could deform the interval into another path like this one. Notice that the 2 intersections at 4 cancel out because the particle reverses direction. any path that starts at -2 and ends at +2 will have an oriented intersection number of 1 with the orange zero sphere. Often, we'd like to talk about linking with respect to a single point. For example, here we'd like to say that the origin is linked with negative and positive 2. There's a trick we can use to do so. When we want to talk about linking with respect to the origin alone, we'll imagine the origin as part of a zero sphere where the other point is arbitrarily far away. We've moved the other endpoint out of the range of the path, so all intersections must occur with the origin. For any path, we can always move the other point far enough away so that this happens. Let's see how we can use linking to show an equation has a solution. Consider the equation 6t to the 5th minus 32t squared plus 33t minus 3 equals 0. Suppose we want to know if this equation has a solution for t between 0 and 1. We can think of t as time, and the left-hand side of the equation as describing the path of a particle. From the animation, we see that the particle crosses the origin, so the equation does have a solution. However, we could have also come to this conclusion just from the endpoints of the path. The endpoints are -3 and 4, which are linked with 0 and 5. From this linking and our trick, we know that any path that starts at -3 and ends at 4 must have an oriented intersection number of 1 with the origin, so there is at least one solution. Let's move on to 2 dimensions. In 2D, a loop can be linked with a zero sphere. This means any membrane with the loop as its boundary must also intersect the zero sphere. By symmetry, it also means that any path with the zero sphere as its boundary must intersect the loop. The next example is a system of equations in 2 variables. We can pack the left-hand sides into a continuous function that takes in a 2D point and outputs a 2D point. We are interested in whether the function takes on the value 0, 0. We can use the plane to visualize the function. For a given input point, which I'll color purple, we can plot the output point, colored blue. For example, if we plug in 2, 0, we get out -6, 0. We are looking for a point where we get out 0, 0. Let's look for a solution inside this disk of radius 2. When we apply the function, it will deform the disk. If the system has a solution, the image of the disk will intersect the origin. We'll apply the 2D linking principle. As the input travels along the boundary of the disk, the output will trace out a loop. The disk will be mapped to some surface with this loop as its boundary. Whatever this surface is, it has to intersect any zero sphere linked with the boundary. We can take, for example, the zero sphere consisting of the points 0, 0 and 0, -2. We'll use the same trick as before and move the point at 0, 2 really far away. This won't change the linking number, and it will also ensure that all intersections occur only with the origin. Therefore, we can conclude that the image does intersect the origin and there's a solution inside the disk. Before the final example, I'd like to briefly discuss another phenomenon known as winding. Consider the following loop along with the origin. If we imagine an arrow with its tail at the origin and its tip traveling along the loop, it will sweep out 2 full revolutions. We say that the winding number of the loop about the origin is 2. A common way to compute the winding number is to calculate the oriented intersection number with the ray emanating from the origin. The idea is that each time the arrow winds around once, it will line up with the ray. When this happens, the tip of the arrow intersects the ray. We can replace the ray with a really long line segment, and this won't change the number of intersections. But now this is just computing the linking number of a loop in a zero sphere. So just like linking is related to wrapping in 3D, it's related to winding in 2D. The winding number is just computing the linking number with respect to a single point. The last equation I want to look at is f of x equals x. Here f is some continuous function from the disk to itself. That means if you plug in a point inside the disk, you get out a point inside the disk. A solution to the equation is a point that ends up in the same spot after applying f. It turns out that for any such f, there's always a solution. This is Brouwer's fixed point theorem. We'll demonstrate this theorem using winding. Instead of f of x equals x, we'll use the form f of x minus x equals 0. Now our usual method would be to show that the image of the disk's boundary is linked with the origin. But now we've seen that we could also show that this image has a non-zero winding number with respect to the origin. We'll translate the green arrow so that its tail sits at x. Then its head is at f of x. Since they're the same arrow, we can instead show that the blue arrow sweeps out one revolution. We'll do this by comparing the blue arrow to a new arrow with its head at the origin. We see this orange arrow sweeps out one full revolution as x travels along the boundary. Also note that the orange arrow makes an acute angle with any other arrow pointing inside the disk. In particular, it makes an acute angle with the blue arrow. This means that as x travels around the disk, the blue arrow can't stray too far from the orange arrow, and it makes one full revolution as well. So we see that the blue arrow has a winding number of 1, as we wanted to show. We've only scratched the surface of linking and its applications in this video. For example, you might be interested to learn how the fundamental theorem of algebra can be proven using linking. I've included some additional resources to learn more. I'd also like to acknowledge visual complex analysis, which is the source of the argument presented for Brouwer's fixed point theorem.